All right, welcome to this explainer. I want you to just imagine, for a second, millions of tons of steel moving at incredibly high speeds, literally crisscrossing the continent day and night. Have you ever wondered what actually keeps these massive trains from colliding with each other? Well, the answer is railway signaling. It's this intensely high-stakes world where absolute uninterrupted power isn't just some nice-to-have convenience. It's quite literally the only thing standing between safe passage and utter disaster. So today, we're unpacking the ultimate fail-safe engine behind all of this, the integrated power supply, or as we'll be calling it, the IPS.
Here's our game plan for this explainer. We'll kick things off with the major vulnerabilities of the older grids, then we'll introduce the IPS solution itself. After that, we'll trace exactly how power flows through the system, check out the emergency fail-safes, and finally wrap up with the very strict environments needed to maintain it.
Okay, Section 1, the conventional power problem. Let's wind the clock back a bit and look at the absolute chaos railways used to deal with. Historically, conventional railway signaling relied on this totally scattered mass of individual batteries and chargers. I mean, it was incredibly bulky, it was a nightmare to maintain, and worst of all, it completely lacked fail-safes. If a single module failed, your track signals could just go dark, right? No warning. Contrast that with the integrated power supply. This thing is a centralized, completely modular system. Instead of chaos, you're maintaining a single battery bank, which drastically cuts down on downtime, and it comes with built-in inverters that guarantee uninterrupted signaling. It's a real game changer.
Moving right along to Section 2, Meet the IPS Solution. Let's actually get to know the hero of our story here.
Just take a look at the physical footprint of these towering units. The IPS cleverly consolidates all that massive power capability into a sleek, highly organized frame. And because it's built on a modular design, technicians don't have to rip apart a whole room of wires when something breaks. Nope, they simply slide out a faulty nodule and slide in a fresh one. It's kind of like a giant high-tech Lego set. It's just a remarkably elegant solution to what was once a very chaotic problem. But of course, a system this robust wasn't perfected overnight. This technology was forged through intense trial and error out in the real world. The primary specification, which is known as RDSO/SPN/165, started out as version 1.0 way back in January 2000. And over the years, actual field problems really drove its continuous evolution. So version 2.0 comes out in 2004 to tackle major issues based on management recommendations. Then throughout 2005, you see multiple amendments made to drastically boost reliability, doing things like standardizing the alarms and adding very specific ventilation requirements for the modules. All of that hard-learned experience culminated in the highly refined version 3.0 that was issued in 2012.
Which brings us to Section 3, How Power Flows Through IPS. Let's actually track how this system breathes life into the railways.
So let's trace the journey of a single volt. The grid outside, it's chaotic. So the IPS essentially acts as a massive stabilizer. Step 1. You've got this wildly fluctuating input of anywhere from 150 to 275 volts AC entering what's called the switch mode rectifier, or SMR. Step 2. The SMR grabs that unpredictable power and converts it into a perfectly steady, reliable 110 volts DC. And then, Step 3. That clean 110-volt DC is intelligently deployed out to 3 subunits. It charges the massive battery banks, it feeds the online inverters so it can be converted back into AC for the signals, and it flows right into the DC bus bar to power various internal converters.
Now, a really absolutely crucial point here is how the system handles the very first major component on this journey, the FRBC, or Float Rectifier Cum Boost Charger. I know, it's a mouthful. Basically, this is the module responsible for charging and monitoring the battery bank, but the real magic phrase to remember here is N+1 modular design. So what does that actually mean? Well, think of it like having your star backup player already geared up and out on the field. You have the exact number of modules you need to run the system, that's your N, plus one extra module that's already powered on and actively sharing the load.
Looking at the actual FRBC rack, you can totally see how this N+1 hot standby design works in practice. Because if one of these active modules just suddenly decides to burn out or fail, there's no panic. That active backup instantly takes over the remaining load without a single hiccup. The trains quite literally keep rolling.
Okay, next stop on the power's journey is the ACDP, or AC Distribution Panel. This is the part that translates that DC power back into AC to actually light up the track signals out there in the real world. And it features incredibly precise regulation, making sure the output stays at exactly 230 volts AC within a razor-thin 2% margin. It also boasts this lightning-fast auto changeover arrangement. If the inverters happen to fail, the system triggers a backup constant voltage transformer in just 500 milliseconds. That is half a second, folks, ensuring those track signals never ever go blank.
You can easily spot the AC distribution panel by its bright blue inverter and automatic voltage regulator modules. Now, both inverters are normally powered on, but only the main one actually connects to the load. They use something called pulse width modulation, which basically means they're rapidly switching the signal on and off to guarantee a perfectly steady output that is totally immune to overloads and short circuits.
And finally, we have the DC distribution panel, which caters to the system's DC power needs, operating incredibly smoothly even if there are massive internal voltage fluctuations anywhere between 98 and 138 volts DC. But here is the really crazy part. For the highly critical relay internals, the IPS actually upgrades to an N+2 strategy. So there's an active hot standby sharing the load and a completely separate cold standby that's powered down but physically installed and ready to deploy. It is just layers upon layers of bulletproof redundancy.
Right, moving to Section 4, Alarms and Emergency Failsafes. What actually happens when the worst-case scenario arrives?
Picture this. Grid power has completely failed. The system is surviving entirely on its battery bank. As that battery drains, which is measured by depth of discharge or DOD, the tension really starts to rise. At a 50% drain, a red alarm blares, start the generator. At 60%, a new, more urgent alarm screams, emergency start generator. Then, at a 70% drain, the system makes this brutal calculated sacrifice. It completely cuts off the signal feed to save the core, though it keeps the DC to DC converters running. Finally, at a critical 90% drain, it literally sheds its limbs to keep the brain alive. It cuts off all DC to DC converters to protect the batteries from permanent, irreversible damage, leaving only the absolutely vital communication lines intact.
Finally, Section 5, Ideal Setup and Maintenance. Because honestly, all this brilliant engineering is useless without protection.
You might think a system this tough could just be thrown into some dusty basement, right? Actually, it's quite the opposite. The IPS requires incredibly strict environmental controls. The room literally must have ceramic floor tiles to prevent dust and static buildup. You have to enter through double doors so they act as an airlock against dirt. There have to be fresh air fans outfitted with special dust dampers. And those massive batteries? They're so volatile, they actually have to be housed in a completely separate room with dedicated exhaust fans. Plus, manual maintenance is still very much required, from checking electrolyte levels to running regular cell retentivity tests. The machine takes care of the trains, for sure, but we humans still have to take care of the machine. Which brings us to our final thought for today. We've seen how the integrated power supply takes chaotic, unpredictable energy and transforms it into a perfectly synchronized, highly redundant lifeline for our railways. It's built to systematically sacrifice itself to prevent a larger disaster, relying on those brilliant hot standbys and modular failsafes. But it really makes you wonder, if this kind of modular N+1 redundancy can keep millions of tons of steel moving flawlessly across the country without fail, where else in our modern infrastructure could this exact architecture prevent a total disaster? What about our hospitals, major data grids? The principles we've explored today go far, far beyond just the train tracks. Thanks so much for joining me on this explainer, and keep questioning how the hidden systems all around you are built to survive.